would like to welcome all the listeners to this lecture series. In this lecture, I would like us to revisit the concept of finite sets, denumerable sets, also called countably infinite sets, and we shall also look at the concept of countable sets. The essence of this is to make sure that clarity in understanding finite sets, denumerable sets, and countable sets is put forth to the viewers, because these concepts at times get some students thrown off balance, get some students confused. So for that reason, I've decided to see if we can give a little touch to it. And to start, I would like us to first of all look at the ingredients that will enable us understand these concepts. So we shall start with review of other important concepts that are associated with the concepts we intend to discuss. Here, I would like us to start with the review of what I will call, what we know as one-to-one or injective functions. This is the first one we shall look at. Then we shall also look at onto or surjective functions. Then the concept of bijective functions. So these are the first three things I would like us to review before we get into a discussion on the topic at hand. Now let us start as follows. Given two sets, say A and B, a function f from A to B is called a one-to-one function. Remember, one-to-one function is also known as injective function. So a function is called a one-to-one function if and only if given x, y in A. Here I'm assuming that the domain of the function is A. Given x, y in A, we have that x not equal to y implies f of x is not equal to f of y. What this means is that distinct elements have distinct images. An alternative way of saying this is nothing but saying it in the line of the contrapositive of this statement. I may say equivalent. For that reason, I can say equivalently, f from A to B is 1-to-1 if and only if for x, y in A, f of x equals f of y implies x equals y. So assuming I label here 1 and label here 2, 1 and 2 are contrapositive statements, and therefore they are equivalent. And that gives us a way of showing that a function is one-to-one. So to show that a function is one-to-one is either we're able to show that one holds or that two holds. That is to say, if we can show that distinct elements have distinct images, then we are done. If we can show that whenever images of 2 points are the same, then the 2 points are the same, then that also justifies that the function is one-to-one. Now let us quickly look at this example. If we consider n the set of natural numbers, the counting numbers 1, 2, 3, 4, and so on. N is the set of natural numbers, and E is the set of even numbers 2, 4, 6, 8, and so on. So if we consider these two sets and we define consider these two sets and define f from n to e by, say, define f from n to e for any n we pick in n by f of n equals to n. We can easily see that the function f defined this way is one-to-one. This is because then f is 1 to 1. This is because given n1, n2 in n, we see that n1 not equal to n2 implies that 2n1 is not equal to 2n2, and this implies that f of n1 is not equal to f of n2. So whenever n1 is not equal to n2, it is clear that 2n1 is not equal to 2n2. But 2n1 by definition is f of n1, and 2n2 is f of n2. Since 2n1 is not equal to 2n2, it means that f of n1 is not equal to f of n2. Therefore, n1 not equal to n2 implies f of n1 is not equal to f of n2. Thus, the function f defined from n to e, given for all n in n by f of n equals to n, is an example of a one-to-one function. Another example is the following. Example. If we assuming that we are given a to be equal to the interval 0, 1, and b to be equal to the set R of real numbers. Given these two sets, then the function f from 0, 1 to R defined for all x in 0, 1 by f of x equals x over 1 minus x. F of x equals x over 1 minus x is a 1-to-1 function. To see this here, to check this, and remember, we were able to establish the definition of that these two. I was able to remember saying that these two, 1 and 2, are equivalent. And in the first example, I made use of 1 to check that this function is 1-to-1. Then in this particular, in the second example, I would like to make use of 2. That is the contrapositive statement of the contrapositive of 2, to check that the function f given by f of x equals x over 1 minus x from 0, 1 to r is 1-to-1. To see this, I want us to observe that for any x, y we pick in the interval 0, 1, for any x, y we pick in the interval 0, 1, f of x equals f of y implies x over 1 minus x equals y over 1 minus y. This implies that x into 1 minus x is equal to y into, x into x into 1 minus y is equal to y into 1 minus x, which implies that x minus xy is equal to y minus yx. Of course, we know that xy and yx are the same because of the commutative property of multiplication in R. This means, therefore, that this implies that x is equal to y, because if we add xy to both sides, and this we cancel out this, we have x equals y. This means, therefore, that f of x equals f of y implies x equals y. So that function f from 0, 1 to r given by this formula is a 1-to-1 function. The next definition which I look at is the definition of an onto function. A function f from a to b is called an onto function or surjective function, if and only if for any y we pick in B, where B is the range of the function f, there exists x depending on y in A, such that f of x sub y is equal to y. So this is what it means that to say that f is onto. F is onto whenever it is such that if you get to the codomain or the range of the function, in this case I'm assuming that B is the codomain of the function. If for every point in the codomain, which is for every point in B, we can find a point in A which f sends to y. That is to say, every element of B is an image of a particular element in A. That is what it means to say that f is onto. A typical example, in fact, okay, let's see examples. Let us even look at the example I gave, this particular example I gave up here. That is, these two examples. It happens that coincidentally the two examples solves our problem. The two examples above will still do the job. Example, the function f from n to e defined for all n in n by f of n equals 2n is an onto function. Is an onto function. Is an onto function. This is trivially true. This is because for any y I pick in E, there exists ky in n such that 2ky is equal to y. Why is this so? This is because E represents for us. Recall that n is equal to the set of natural numbers 1, 2, 3, and so on, while E is equal to the set of even numbers 2, 4, 6, and so on. So this statement is true because since any y I pick in E is an even number, and since an even number, it means that it is divisible by 2, and since divisible by 2, it means that we can find a number in the set of natural numbers so that this even number can be represented as 2 times that number we found in n. So, in fact, it's true because every even number can be written in this form, where ky is a natural number. Please, let us be careful here. This k is k sub y, not k times y. K sub y. K sub y. So y in E implies there exists ky in n so that 2ky is equal to y, meaning therefore that for any y we pick in E, there exists ky in n so that f of ky is equal to y. So this means therefore that f is onto. Hence, f is an onto function. Remember that an onto function is also called a surjective function. Let us look at example 2, the other example. The example 2 above. Let's also check that it is also an onto function. The second example, maybe I'll call this one, let me label here 1, then 2. The function f from 0, 1 to r given for all x in 0, 1 by f of x equals x over 1 minus x is also an onto function. It's onto. It's onto. So how do we check this? This is where one to apply a little algebraic trick. But for the fact that I've been practicing this, I can easily do it. Then I'll give you a hint on how I went about it. So this is onto. To see this, observe that for any y in R, there exists, say, u sub y equals, so I can say, now I see I have to really convey the message I'm looking for. I have to reduce the range space so that what I'm talking about will make sense. So we consider the function this time around from to 0 plus infinity. The essence of this is to avoid a certain difficulty I've just observed. The function f from 0, 1 to 0 plus infinity given by given for all x in 0, 1 by f of x equals x over 1 minus x is an onto function. To see this, observe that for any y in R, we can find uy equals, for any y in the interval 0 plus infinity. So what I'm saying is that in this effect is the following. That if we're given the function f from 0, 1 to 0 plus infinity, and given x in the interval 0, 1, if we define this function f by f of x equals x over 1 minus x, then that function f is onto. To see this, if we take y in 0 plus infinity, then there exists uy equals y over 1 plus y. Observe that y over 1 plus y is actually greater or equal to 0, but less than 1 for any y that lies here. As 0 is 0, and at any other thing bigger than 0, it will be less than 1. This means that this uy defined like this is interval 0, 1. And it's such that f of uy is equal to y. So, just a little algebraic manipulation will show that this holds. Because if we look at, by definition, f of x we know is equal to x over 1 minus x. This means therefore f of uy will be equal to u sub y over 1 minus u sub y. And this will give you nothing but y over 1 plus y divided by 1 minus y over 1 plus y. And this is nothing but y over 1 plus y divided by 1 over 1 plus y. By the time this is evaluated, we'll get 1 plus y over minus y over all over 1 plus y. And this will mean, therefore, that this is equal to y. So computationally, this can be gotten. But the question is, what motivated the idea of that? What is the idea behind the creation of this uy to give us this? The idea is going back to the definition of this function and assigning a value y to this and make x the subject. If you assign a value y to equal to x over 1 minus x, you will observe that this will mean that y minus yx will be equal to x. And this means, therefore, that or that y is equal to x plus yx, which is equal to x into 1 plus y. And with this, you'll find out that we therefore get that x is equal to y over 1 plus y. So this x you've gotten this way is the value of x in the interval 0, 1. So it's from the given function that we're able to construct what the value of uy we are looking for should be. This is what we'll call uy in the here, and the image of that uy will turn out to be y. So the essence of doing this is for the listeners to know that, in fact, the targeted audience to know that all these things do not fall from heaven. It's a matter of taking your time to do a lot of exercises, and you'll get things going. So that function given this way is onto. Now observe that initially I wanted to take exactly this one, but I observed that it's not necessarily onto, because if I'm given this one is an onto function, that because of the restriction on the range, it goes from 0, 1 to 0 plus infinity, while we've shown is an onto function. This particular one is not an onto function. The reason is because I can find a value here for which there is nothing here that will be mapped to it. Observe that by this definition, that this particular value is always bigger than or equal to 0. It's always bigger than or equal to 0. So if I take a negative value here, we may not be able to find something here that will be mapped onto the negative value by this function. And that is why, for instance, to see it clearly, you'll find that assuming that here is the entire ray line, and I do this kind of construction, you'll find out that if I take y a negative value, then y over 1 plus y is necessarily negative. Y over 1 plus y will be negative. For example, if we take y to be minus 2, if we take y to be in the interval minus between minus 1 and 1, say y equals minus half, you will see that this will give us minus half over 1 minus half, and that will give us minus half over half, which is minus 1, and minus 1 is not here. So that's it. So we have to be very, very careful when we're handling all these things. Now let us give more examples. Another example of another example of functions that will fall within what we are looking at is consider the function f from R to R defined for all x in R by f of x equals the e raised to the power x. This is the exponential function. I want us to observe that graphically this function, this is r cross r. The graph of exponential function is something like this. Is asymptotic to this x-axis and straightly moves to infinity. It cuts the y-axis at the point 1 because the image of 0 is 1. E raised to the power 0 is 1. So this is the graph of f of x equals graph of f of x equals e raised to the power x. This particular function I've drawn, this particular function given, this function f is 1 to 1. 1 to 1. The reason is because since f is 1 to 1, since x not equal to y implies e raised to the power x is not equal to e raised to the power y, which means that x not equal to y implies that f of x is not equal to f of y. But why did I bring in this picture? I intentionally bring in this picture to explain something. You recall that in graphical representation of functions, that this we have several lines that are parallel to the horizontal axis. So what I want to point out here is that if you look at this curve we've drawn, the graph of the function f of x equals e raised to the power x, you will observe that that particular function cuts horizontal lines at one point at most. It cuts the horizontal line at most 1 point. So geometrically, a function f is 1 to 1 if it cuts the horizontal lines at most 1 point. So this function, you'll find that at any horizontal line you take, you'll find that it cuts it at most 1 point. If you take a horizontal line down here, you'll find that the curve cannot touch it. But any horizontal line above the horizontal axis, the curve will cut it at only 1 point.